Okay, I'm giving this long rambling introduction to deep inelastic scattering. So the point of view we have is that there is a nucleon sitting at rest and there is an electron. In principle it can be a muon also. By the way, I should mention that in the mid-80s at CERN they performed scattering of muons on protons and nuclei. There were 3 experiments. One is called European Muon Collaboration Experiment, EMC. Then there was New Muon Collaboration, and then there was Spin Muon Collaboration. All of which provided some interesting data on the structure of proton. So I keep saying electron because most of the experiments are used electrons, but in principle it can be muons also. So there is an initial electron with 4 momentum k and a final electron with 4 momentum k prime. I believe I have been using k and k prime, not k1 and k2. Okay. And there is an initial proton. Okay, I should call it nucleon. It can be proton or neutron with 4 momentum p. Of course, this p is this initial particle is at rest, and there is both being charged particles, they exchange a photon. Photon has 4 momentum q given by k minus k prime, and after absorbing that 4 momentum, what happens to this nucleon we don't care. So the given kinematical variable is the initial energy of the electron that is known to us, and measured kinematical variables are E prime and theta. E prime is the energy of the final state electron, and theta is the angle between the initial momentum of the electron and the final momentum of the electron. So these are the kinematical variables that are measured in the experiment. And during the discussions in the last 2 classes, I have calculated this quantity, and we showed that this is d omega is, so this is 4 pi alpha square by r. Okay, this then becomes 5 alpha square by e square sine power 4 theta by 2 times w1 cos per. 2w1 sine square theta dot. So, all our ignorance about what is happening after the nucleon observes this off-shell photon is encoded in these two functions W1 and W2. And this I mentioned, this term is the pure Rutherford scattering. So usually when we talk in terms of this, when we consider this cross section, this is sort of what is called modded out. The Rutherford term, it is assumed it's there. We won't explicitly consider the dependence, and we look at the dependence on theta and d prime of the rest of this. And in general, W, by the way, first the fact that this whole thing depends on these two independent functions W1 and W2, that is based on two factors, two features. One is the Lorentz covariance of matrix elements, and second is the electromagnetic gauge invariance. These two constraints limit the number of possible functions to just two. And we ask the question, okay, fine, there are two functions, but do they have some physical interpretation? And to understand the physical interpretation, we consider the so-called elastic limit, where we have not in the above we were considering a general final hadronic final state, but here we limit ourselves that there is the same nucleon that is there in the initial state is also there in the final state. In that elastic limit, there is a constraint between E prime and cos theta, and that constraint is written in the form where Q square, of course, is K minus K prime whole square, which is approximately minus 4 E prime sine square theta by 2, and mu is equal to T minus E prime. By the way, we can also write 2m nu as 2p dot q. So the elastic constraint is q square plus 2 p dot q is equal to 0. In this limit, we find that, by the way, this W1 and W2 in general are functions of E prime and theta, or equivalently, instead of E prime and theta, we can exchange them with these two variables, q square or nu, or equivalently, we can exchange them with the two variables q square and 2p dot q. Thus, q square and 2p dot q, they have the advantage of being Lorentz invariant variables. So, they have the same value in whichever Lorentz frame I look at them. So, this W1, which in general is a function of q square and nu, is, because of this constraint, I have a delta function times dot dot dot, and similarly for W2, and this I discussed in the last class. This quantity which occurs in the square brackets is a linear combination of the electric and magnetic form factors of the nucleon, and similarly this is a different linear combination of electric and magnetic form factors of the nucleon. So this W1 and W2, they have the interpretation that in the elastic limit they are related to the electric and magnetic form factors. These two kinematic quantities, q squared and nu, we argued that they are Lorentz invariant, but they carry some dimension. They have some dimensions of energy, and we would rather use quantities which are dimensionless. They are sort of more easy to handle, so to speak. So we will make another transformation and rewrite that expression d square sigma dq square rather d square sigma de prime d cos theta. First we will write it in the form d square sigma dq square d nu, and then we will make one more change of variable and write it in terms of two dimensionless variables. So first okay, let me introduce dimensionless variables. One of them is minus q square by 2 mu nu, or minus q square by 2 p dot q, and you see that this is And the second variable we introduce is y, and y is defined as mu by e. So this is e minus e prime by e, or 1 by. Of course, this looks as if it's not Lorentz invariant, but this is also Lorentz invariant because I can always write this as P dot Q by P dot K. P is M0. So P dot Q is M times E minus E prime, and P dot K is M times E. So Y is also defined, can be defined easily in terms of Lorentz invariant variables. So Y is also a Lorentz invariant quantity, and you see that once again Y is 0 less than 0. It is bounded by 0 and 1. Y equal, oh, what did I write here? So y equal to 1 means the full energy of the initial electron and the final electron, they have the same energy, and y equal to 0 means the initial the final electron has taken, oh sorry, no, my mistake, sorry. Y equal to 1 means E prime equal to 0, which means the final electron is at rest. I mean, of course, E prime equal to 0, final electron of course will always have its rest energy, but remember we are talking of energies of order GeVs and we neglect the electron mass. So in that limit, the final electron has 0 energy. It becomes a non-relativistic electron. Whereas y equal to 0 means the final electron has essentially all the energy of the initial electron. Now, this is a fairly straightforward exercise in doing it's a fairly straightforward exercise in computing the Jacobian, and if you do so, you find that dx dy is equal to E prime by E times 1 over 2 pi by m d omega dE prime. And I urge you to work this out, convert the variables, or d omega I write d phi d cos theta, and d phi I can cancel with 2 pi. So this is E prime by E 1 over 2 m d cos theta dE. So you try to change from d cos theta dE prime into dx dy and you get these factors. And also we introduce a couple of more definitions. If you remember, our d square sigma d prime d cos theta we wrote in terms of w1 and w2, but now I define two other functions which are quite straightforward. M times w1 q squared of nu is equal to g1 of x comma y, and mu times w2 q squared of nu is equal to g2 times x comma y. And now here the way these functions g1 and g2 are looked at, we think of, if you go through this argument, naively speaking, we should think of them as functions of x comma y. However, people actually look them as functions of x comma q square. See, there is mathematically the whole thing is consistent. The reason being that I have two variables e prime and theta, and my cross section depends on e prime and theta, and I can use any two other variables which have different dependencies on e prime and theta. And one such variable is q square, and the other variable is q square by 2m nu. So first I change from e prime and theta, I change to q square and nu. And having changed from q square and nu, I say, okay, instead of taking q square and nu, I will consider the dependence on q square and q square by 2m nu. And why am I doing this? Because, let me put it this way. These two variables, they make, quote, physical sense. That way, the variable mu also makes physical sense. It is the amount of energy that is lost by the electron, that is the amount of energy given to the hadronic system. But we prefer to look at the hadronic system using the two variables q square and q square by nu rather than q square and nu. And of course, the reason why we are looking at q square is obvious, because that is the amount of sort of impulse being delivered to the hadron system. It's the Lorentz invariant. It quantifies the Lorentz invariant impulse that is being delivered to the hadron system. So in that sense, q square is an important variable, and we consider the variable q square by nu as our other variable because of this relation. Because q square by nu occurs in the definition of x, and x is what we are defining as the inelasticity parameter. It is telling us how far away is my kinematical system from the elastic limit. So in that sense, we think of x as an important variable, and of course in quantum field theory, q square is always an important variable, that is quantifying the amount of effect the two parts of the interacting system have on one another. Whether it is elastic, inelastic, it doesn't matter. Q square quantifies the effect that one part of the system has on the other. So that's why we keep q square as one of our kinematic variable. And the other kinematic variable we use is q square by nu, because it is telling us how far away we are from the elastic limit. So even though we have introduced these two dimensionless variables x and y, when we actually look at the dependence of these two functions g1 and g2 on the kinematic variables, the actual kinematic variables we consider are not x and y, but instead are x and q square. So with these definitions, the differential cross section again I am writing y, but again I warn you that I am using this slightly hybrid notation. As far as kinematical factors which are appearing explicitly, I am using the variables x and y. But as far as kinematical factors which are hidden in these two properties g1 and g2, which are describing the deep inelastic scattering, I am considering them as functions of x and q square. All this is being done with hindsight, keeping in mind Feynman's Parton model, but not only Feynman's Parton model, what we now call QCD based Parton model. We take simple Parton model, we impose a quark structure on it, and we impose quantum chromodynamics, which describes the interactions of quarks and gluons. And in order to, so this picture is slowly built up over about 15 years or so. but it is a consistent picture, and in order to describe that picture in a simple enough way, we are doing it in this form. But strictly speaking, I should have written g1 x comma y and g2 x comma y, but I have something at the back of my mind, so that is why I am writing this g1 as a function of x comma q square and this g2 also as a function of x comma q square. But important point is this x square y square is pulled out in front, and there is an xy square which is multiplying g1, and there is a 1 minus y times this factor, which is in a given experiment this m by 2e is a constant. So you can call it some constant minus y, which multiplies g2. So now I do an experiment and I measure these cross sections as a function of x and y, and I mod out this x square. Okay, this, if I can, let me rewrite this as 8 pi alpha square by me times 1 over this is some constant k minus y by x square y square So first I look at the whole distribution as a function of x and y, and I sort of try to mod out the term which carries a 1 over x dependence, and I will try to mod out a term which carries this dependence, where this k is 1 minus m by 2. In a given experiment, that's a constant. So that enables me to find what g1 of x is, g1 of x comma q square is, and g2 of x comma q square is. And in general, we expect g1 to depend on both these variables, and similarly we expect g2 to depend on both these variables. But what we find is we find the experimental results show that both these functions g1 and g2, they depend only on x, they do not depend on q square. So they depend only on the inelasticity parameter, they do not depend on the momentum transfer that is taking place. So this was what the experiments, electron proton experiments done at SLAC in 1967, This is what they found. And it was a big surprise that first, why should it be? In general, we expect dependence on both variables, but why the dependence only on one variable? And the second related question is, what is it telling us about the way this off-shell photon is interacting with the proton? And there was a theorist at SLAC called Bjorken. You may have heard his name. He and another man at SLAC called Drell, Bjorken and Drell, they wrote the first textbook on quantum field theory in 1962. And for about 25 odd years, most people learned quantum field theory from those books. And Bjorken gave some explanation based on the popular theory at that time, which went under the name current algebra. By the way, this property is called scaling, and people call x the scaling variable. Sometimes, and Bjorken, in his development of current algebra, he defined an x from a different point of view, which people call Bjorken f, but people denote it by f for some reason. And the variable Bjorken defined turned out to be, if you identify it with this x, you find that everything matches. So this was quite a puzzle, and in 1972, Feynman proposed this Parton model could very simply explain why this G12, rather G1 and G2, instead of depending on two variables x and q square, they depend only on x. So let us see what this Parton model says.
In general, G1 and G2 are function of x and q square. X is q square by nu.
2 and nu.
So yeah, that means these G are only dependent on nu.
No.
Since x
no, they are dependent on x.
Yeah, but x is q square by 2 and nu,
right?
And there is no q square dependence.
No, but this is where you have to sort of keep a very clear idea of what is happening. There are two final state variables, E prime and theta. And we have q square is equal to minus 4 E prime sine square theta by 2 and mu is equal to E minus E prime. Now I define, instead of E prime and theta, I go to q square and q square by minus q square. That is, I use minus 4 E prime sine square theta by 2 and 4 E prime sine square theta by 2 divided by m E minus E. So instead of E prime and theta, these are the two variables I use. And I find that the functions depend only on this variable, they don't depend on this variable.
So still they are dependent on both E prime and theta.
They are dependent on both E prime and theta, yes. But only in this combination. But not in this combination. I am defining two independent combinations of E prime and theta, and things depend on this combination but not on this. But mind you, and this is where you have to keep your eye on the ball, so to speak. In coming up to G1 and G2, I am modding out a lot of kinematic factors. And in modding them out, I am not using these two variables. I am using this variable and the y variable. But that is well known, well understood kinematics. So I don't want to get bogged down by those things. So that is why I'm sort of trying to play this juggling game. In the first step, I use the variables x and y, and having gotten what I wanted, now I forget about y and I start using the variables x and q square. Now, let's go back to Rutherford. In the case of Rutherford, we expected, the The original expectation is atom is some kind of watermelon and alpha particle goes through it, and as while going through it will interact with the inside of the watermelon in some way. But that means that there is nothing in the watermelon which can give enough of a push to the alpha particle to make it go off at a large angle. And when you see such a thing happening, you have to assume that there is something within that watermelon which is giving it such a push that it is pushing the watermelon, pushing the alpha particle in a completely different direction. But of course, one big difference there is whatever that quantity is, it's very massive, so that it is not affected by itself. The gold foil is still there in the Rutherford experiment. The gold foil didn't disintegrate. But here, the picture is different. First, there is something in the proton which is creating enough force on the electron to push it off at a different angle. But in doing that push, whatever it is in the proton itself is affected and is coming out of the proton, and in doing so is making the proton disintegrate. That is the first point. And the second point of this picture is that, okay, you picture the proton as consisting of a large number of such point particles inside, each of which is capable of exerting a force on the electron. But these large number of particles which are inside the proton, they themselves are not interacting with each other. So these are the two key assumptions of the Parton model. Alright. Okay, I'll use the word particles. now we can show in a quite straightforward fashion that with these two assumptions, if we do a calculation, we reproduce the features that are seen in deep inelastic scattering. For that, let us so we draw the same picture as before. You have electron of energy k and electron of energy k prime, and there is an off-shell photon of energy q. But now so I have the initial proton, which consists of a large number of non-interacting partons, and this photon, which is penetrating, whose de Broglie wavelength is small enough that it penetrates inside the proton. I mean, this is a pictorial way of talking, but it interacts with only one of those partons and knocks it out of the proton, so that forms a separate hadron. And the rest of the partons, because one parton is missing, it's no longer a proton. So they somehow combine with other particles to form other hadrons. That is the picture. So kinematically, the leptonic part is the same. But how about the hadronic part? So we said the nucleon has momentum p, which we wrote as m00. But now we say that this parton has momentum x times p, and this parton will have momentum x times p plus q. Fine? I mean, this is assumption I am making, that this photon is interacting with a single parton, and if I say that there are many partons in the proton, each one carries a fraction of the momentum of the proton, so that the sum of all these x's, it should add up to 1. And x by definition is a number between 0 and 1. And by my assumption, if the photon is interacting with only one parton, then the final state parton should have momentum xp plus q. Now, this is simple QED. I have two charged particles interacting with each other through the exchange of a photon. I know the momenta of the initial particles, I know the momenta of the final particles, and I compute the scattering cross section. And if I do so, you find the so if you remember, in computing the this d sigma we wrote as product of leptonic tensor times hadronic tensor. Leptonic tensor, we knew exactly what it was. We didn't know anything about the hadronic tensor. There we used Lorentz covariance, electromagnetic gauge invariance to guess a form of the hadronic tensor, and that's where how that W1, W2 came to be defined. Here the leptonic tensor is exactly the same, but we assume that this Parton has spin half. That's an assumption right now. It has to be justified. But if we assume that this Parton has spin half and some charge, then it's straightforward to write down the hadronic tensor based on our knowledge of QED. So we can write it down to be this H alpha beta is 1 over 4 in order to follow the chain and link, I use this symbol xi. Yeah. Sum over spins dq. This is what I call prime. This I'm writing in a slightly complicated form, but this simplifies to 1 over psi m sum over spins u bar psi p gamma alpha u p prime u bar p prime gamma beta u p or rather u psi p times delta p naught prime minus psi p naught minus q naught by 2 p naught prime. Yeah. So this expression for the hadronic tensor, we have to do the summation over all the final state phase space, and that is how this factor occurs. And when we do this integration, it leads to this delta function, which is just the energy conservation delta function. So this is the phase factor which comes because we need to sum over all the possible final states, and then when we do the integration, that leads to this energy conserving delta function. And these rest spinners, they are straightforward from the Dirac algebra. And now this energy conserving delta function, which I have written in terms of P naught prime and P naught, I can rewrite it in terms of Lorentz invariant variables, and when I do that, you will find that this fraction of the momentum carried by the Parton is equal to that inelasticity parameter x.
Where is the integration?
Sorry?
The integration symbol is, you have to integrate right from the first.
Yeah. No, okay, I should have put an integration symbol here. I have integrated over this dqp prime.
Okay.
I have integrated over all possible final state momentum. Oh, sorry. There is a mistake, which is why this called. There is a confusion. Times the energy momentum conserving delta function. I forgot to write that. P prime minus psi p plus q. Sorry, that should have been. And now dq p prime will take care of the momentum delta function, leaving behind the energy conserving delta function. Yeah. Now, this delta function, I rewrite it in terms of Lorentz invariant quantities, and this is a bit of a mathematical exercise. Delta P naught prime minus xi P naught minus Q naught divided by 2 P naught prime is equal to that theta function is there to indicate that P naught prime has to be positive because it has the interpretation of energy, times delta of P naught prime square minus z P naught plus Q naught whole square. This delta function of P naught prime, I wrote it as a function, delta function of P naught prime square. So that took care of this. But this is theta P naught prime times delta of P prime square minus xi P plus Q whole square. Why is that? Because there is the momentum conserving delta function I have already taken care of. The momentum conserving delta function is there, which means that this one implies that P prime is equal to xi P plus Q. So I take the mod square of it and subtract it from this, which converts P naught prime square to P prime square. I take the mod square of this, subtract it from this, which converts this to this. And since these two are equal, the argument doesn't change. So because P prime is equal to xi P plus Q. And now if you square this, you will find that this is theta times, instead of P naught prime, I will write xi P naught plus Q naught. And here, this is if I square this, you will find that this is 2m nu times xi plus Q square. This is simple algebra you need to do. If you do so, you will find that if you square this, you have the xi square term will cancel out and you have these two terms left behind, and this of course minus q square by 2 mu is that inelasticity parameter x. So this is theta times psi p naught plus q naught times delta of psi minus x by 2 mu. So we have, so this h alpha beta is delta of psi minus x times sub dot dot dot. Now that W alpha beta, which we considered before, which we wrote in terms of W1 and W2. But now if I consider that W alpha beta in terms of H alpha beta, I have a Parton with carrying momentum fraction xi. But there is some probability for it, which is f of xi. So I can argue that W alpha beta is integral 0 to 1 d xi f of xi h alpha beta of xi. I have a Parton carrying momentum fraction xi, and for that Parton I get the hadronic tensor to be H alpha beta. Now the probability that the momentum fraction carried is xi is f of xi. Now I have all these Partons and I am treating them all to be independent of each other. They are not interacting with each other. So I just sum over all these Partons. For argument's sake, let us say that there are 10 Partons. Parton number 1 carries momentum fraction 0.2. Probability of that happening, let's say, is 0.1. Parton number 2 carries momentum fraction 0.05. Probability of that happening, let's say, is 0.2. So I compute the hadronic tensor for the first Parton multiplied by its probability. I compute the hadronic tensor for the second Parton multiplied by its probability, and I do it for all the Partons. And since I am assuming that there is no correlation between any of the Partons, I just sum over the whole lot. And that's what this is. But H alpha beta has this delta function xi minus x, where x is that inelasticity parameter that we have defined, which implies that this W alpha beta is a function of So this is how Feynman explained the fact that G1 and G2 depend only on X and do not depend on any other combination, in this case Q squared. So the inelasticity parameter is telling us that my probe interacted with a constituent of the proton which carried a fraction of the momentum that is given by the inelasticity parameter. So the two assumptions of Feynman, that there are point-like particles interacting with this off-shell photon, and these point-like particles are not interacting with each other. Both of them, so the second assumption is going in writing this equation, and the first assumption went in deriving this expression for H alpha beta. Putting these two assumptions together, we are able to explain the fact that these W alpha beta, or that W1, W2 are equivalently G1 and G2, which by the way are called the structure functions of proton. They depend only on the inelasticity parameter X. They do not depend on the momentum transfer Q square. So that is one part of the Parton model. The second part of the Parton model is the explicit form of H alpha beta. Here I worried only about the delta function. I didn't worry about how does the alpha look, how does the beta look. If I worry about that also, that tells me whether the partons are scalars or spinors. Here, for argument's sake, I assumed spinors and wrote down an expression, but I didn't explicitly work out what that spinor expression is. I only worried about the kinematics and got this delta function. But if I worry about the spinor algebra and work out the alpha beta dependence, I will get some alpha beta dependence here, and that will tell me whether I compare it with the experiment. So this, if I assume that my partons are scalars, I get one kind of alpha beta dependence, whereas if I assume that the partons are spinors, I will get a different kind of alpha beta dependence. And then comparing it with experiment, I can tell whether the partons are scalars or spinors. You can ask, why can't they be vectors? Well, in principle they can be, but if they are vectors, then the formalism is much more complicated. But anyway, the results show that the partons are spinors. So we consider explicitly we will consider the alpha beta dependence for scalars and spinors, and we will show that data agrees with the spinor assumption. Okay, I will stop now. So in the next class we will consider these additional details of the Parton model and predictions of what is called quark-Parton model for these structure functions. Okay, we'll stop now.
Here in the expression of W alpha beta, so there will be a summation in front over all the partons.
No, but that is this integration. That summation I have converted into an integration. I mean, here, okay, to start with, here I am assuming all partons are of the same type. If there are different types of partons, then I have to sum over the different types also. But here I have assumed that all partons are of the same type.
So, does this model give any value or bound on the number of partons?
No. It does not give any bound on the number of partons. But, well, I will discuss the details in the... It gives some interesting results and they have been experimentally verified. Let me leave it at that, and I will discuss those details in the next class.
You said partons are spinors.
Yeah.
That means gluons are not.
We will discuss those details. I mean, whether you want to call gluons partons or not, that's a question we will address in the next class.
And what motivated Feynman to, like, did he knew that when he would include such point-like particles inside the proton, he would find that the W alpha beta would be function of X only?
Yeah, in some extent. Here I must confess I have not read Feynman's original papers. So, but at least this discussion seems to indicate that yes, he had an inkling that, and which is actually follows from, to some extent, from Rutherford, that things depend only on the so-called inelasticity parameter and not on the momentum transfer. I believe that sort of gave some hint that there is some hard particle, that what is called a hard interaction taking place. I mean, people use these terms, hard interaction and soft interaction. Basically, the hard interaction sort of implies the projectile undergoes a large momentum change, whereas soft interaction means the projectile undergoes small momentum change. That's again a sort of hand-waving definition, but this deep inelastic scattering is characterized as a hard scattering, and a hard scattering usually is an indication of the fact that there is something hard in the target which is exerting a lot of force on the projectile. And so that is I believe that is the main motivation for Feynman to come up with this model.
Comparing with Rutherford scattering, there also comparing with what you just said, hard scattering, big momentum change. In this case, like, how do we see the momentum change?
No, momentum.
Is it because the electron is bouncing back?
Yeah.
But that happens in Rutherford scattering also. So
It happens in Rutherford scattering also, but no, there are different aspects. So the analogy between deep inelastic scattering and Rutherford scattering is not exact. Rutherford scattering is an elastic scattering, and this is a quote. By definition, this is deep inelastic scattering. But of course, Feynman was interpreting deep inelastic scattering as some kind of elastic scattering process between the electron and the parton. And I believe the point of view is, if you see a very large angle scattering, I have a stationary target and a high energy projectile, high momentum projectile, and if in such a situation, if the projectile changes its momentum by changes its direction by a large angle, then there is something in the target which is capable of exerting a force which can make it change by that large angle. What is that? So that is how the question is posed. And if you think of a proton as a sort of something mushy, the proton cannot do that. So one has to think of something in the proton which is point-like and which is exerting this large force. See, we know that proton has a size of 1 Fermi. So if you think of the charge in the proton being distributed over 1 Fermi, let's say you make up a picture that proton has uniform charge density. It's a sphere of uniform charge density. Or even if it is not sphere of uniform charge density, okay, you say, okay, it has some exponentially decreasing charge density, large charge at the center and exponentially decreasing charge. Some picture you make up. And you ask, can such a charge distribution impart enough momentum change to an electron to make it come out at 90-degree angle? And the answer turns out to be no. Whereas if you assume that the proton consists of 10 point-like charges, each 1/10 the charge of proton. Now you are talking about point-like charge, which means that the electron can go as near as possible to that point-like charge. And so when it goes to a distance of 1/10 of a Fermi or 1/20th of a Fermi, the Coulomb force exerted by this parton on the electron is large enough to make it deviate at 90 degrees or 120 degrees. So that is where the analogy with the Rutherford scattering is.
In Rutherford scattering, we estimate the size of the nucleus.
Yeah.
Here, do we have an estimate of size of partons?
No. That size of the nucleus was estimated based on some hand-waving statistical arguments. But here, of course, one is doing something much more. So people have asked that, okay, let me assume that the Parton have some size and work out the consequences. People have done that and they have set limits. Rutherford was 120 years ago. So since then, we know much more about how to do these calculations. So there are the same way proton size is estimated. One can develop that further, and one can try to ask what are the sizes of the partons. And so far there are only upper limits. So we have not found a definite size for any parton. By the way, there is something called proton radius puzzle. So the size of proton estimated from two different experiments, the answer is coming out to be different. So that's a open problem in physics, goes under the name proton radius puzzle. But as far as partons are concerned, similar techniques are applied to partons, but so far no size of parton has been found.